Okay, example 5.21. We are given a surface sigma consists of a cylinder in the first two octane. Okay, we have a sigma cylinder given by x squared plus y squared equal to 9. The first two octane. Okay, so let us first two octane meaning that it should be so. Now we draw the first two octane is basically, so we draw a complete cylinder with a circle radius 3. So this one is Z. So when we have a first two octane, it should be from, okay, so the first two octane means, okay, what we understand with the first octane. First octane means X, Y, Z positive. Okay, that is a first octane. So the first two octane means X can be positive and X can be negative, like this. It coming from the first two quadrant. Okay, so on XY plane, we have the first quadrant and second quadrant. So when we convert into 3D, so we have a first octane where Z is always positive, and also a second octane. So to get a complete sketching should be this one. It becomes half. So it becomes half. So we cut the cylinder into two pieces, so it becomes, so the correct sketching should be like this. This is X, so this is Y, and this is Z. So this one. Okay, so it looks like this, cut into two pieces. See, so only this part. Okay, so read it again. So the surface consists of the cylinder in the first two octane. So that is your surface. This is open surface. Okay, but then they said that first two octane bounded by the plane Z equal to 0. So bounded by plane Z equal to 0, Z equal to 4. So this one is located at Z equal to 4. That's it. Okay. Okay, if, so they give you the vector field. The vector field given is Z, and then XY, and then XZ. So you have to evaluate the surface integral. So you have the curl F dot N ds over the surface sigma given. Okay, so then okay, so meaning that, can we use Stokes theorem? Because they don't mention that you have to use a Stokes theorem. If you don't want to use a Stokes theorem, then you can proceed with the surface integral given, where you have to proceed to obtain the curl F first and then find the normal vector dA. Okay, so now we have to think about the surface. How many surface that you have? It is open, this is not closed. So your surface is the cylinder itself, this one, that is number 2. So the surface, this one, which is part of the cylinder. So that is a sigma 1. What else? So the top here, where z equal to 4. The sigma 2, where z equal to 4. And sigma 1 is given by x squared plus y squared equal to, what is the equation just now? 9. Okay, 9. And you have another sigma 3, where your surface function z equal to 0. So in this case, you have to provide three different surface integral. Okay, where your grad f is the same. No, not grad f, but the curl f is the same, but your n should be different because you have a different surface. Okay. Can we, if you don't want to use if you don't want to compute the three different surface integral, do we have any option to simplify our work here? So if you're thinking about Gauss, it is not possible because Gauss, you have to have a solid, but this is open surface. Okay, so can we use the Stokes theorem? So it looks like we can use, but you have to refer back to the idea of the Gauss. So sorry, the idea of the Stokes. So what is the Stokes say? So the Stokes say that if you have an open surface, and that open surface there is a boundary, and that boundary is given by the closed curve. Can you see the closed curve, which becomes the boundary of the surface sigma? Your sigma is the sigma 1 plus sigma 2 plus sigma 3. So where is your boundary? Can you see that? It should be closed curve, and that closed curve becomes the boundary of your sigma. So where is it? So the boundary, which is a closed curve, is given by this closed curve, right? Can you see that? So you got if you standing over here, you can see on the x plane it is a rectangular region. Okay, so in this case I'm not saying this can be simplified your work, because if you want to apply the Stokes theorem, you still need to compute more than one integral. Okay, so let's say now we want to solve the surface integral here using Stokes theorem. So using Stokes theorem, you have to use the line integral, where your curve is a closed curve, f dot dr. F is given and dr is coming from R. What is R? R is the vector function of the curve C. But then you have to ask yourself, your curve here, how many curves that you have along this line? You got 4, right? So this one, maybe that is called C1. So this is C1, and this one C2, this one C3, this one C4. But I think still simpler than you have to compute three surface integral. Okay, this one you just need the dr, but this one you have to obtain the n and you have to obtain the curl f. But it depends on, because the question here doesn't mention that you have to use a Stokes, then it is up to you. You can proceed with the surface integral, or if you want to apply the Stokes theorem, then you have to compute the line integral. Okay, but if the question saying about you have to using Stokes theorem evaluate the curl f dot nds, then you have to follow the instruction. So now let's say we want to solve using Stokes theorem, where you have to compute the line integral where given by 4 line integral given by C1, C2, then C4, C3 and C4, where your dr should be different, but your f is the same. Okay, so now since you need to, so for okay, look at your closed curve here in pink color. If you want to convert into t, parameter t, then you have to know the limit from t, from which t to which t, right? So you need to have the direction along the curve. So you need the direction. So how can you know the direction, whether you have clockwise or anti-clockwise? Again, we implement the right hand thumb rule. So using your right hand, so now tell me, we are talking about the surface sigma, and we want to say that the surface sigma, on the surface sigma there is n, and n always point outward to the surface sigma. So in this case, our surface sigma is the sigma 1 here, right? Okay, so now your surface is part of the cylinder, which is sigma 1, this one, the surface. So when you want to say that n point outward to the cylinder, it should be point outward to the cylinder, so your direction should be in this direction. So this is your n. Okay, so now using your right hand thumb rule and use your right fingers to determine the direction, and your thumb of your right hand follows the direction of the normal vector. So now you follow the direction on your sketching, so the direction is in that way. Okay, so please follow your own, because this I'm using the mirroring, so it just everything just opposite direction. Okay, so your end point to that way, follow your sketching, and then your 4 fingers telling you the direction. So you can see that the direction is something like this, so it is anti-clockwise direction. Okay, anti-clockwise direction if you looking from this side. Okay, so it looks like we have this direction, we have this direction, this direction. So please double check. So your fingers follow the direction in that color here, and your end point that way, so we have that particular direction. So then your limit of t or x or y that you are using for the r, your rt or your r, sorry, your vector function of the curve should follow this direction. Okay, so now we already have the direction along the C1, C2, C3, and C4. So now it's time for us to compute every single line integral. Okay, so look at the C1. So now we solve for the C1. So when we are talking about the C1, so what is the equation that we have? So remember, here we have to find the dr. Okay, we have to obtain the f dot dr. Okay, so along the C1, so what is the equation that we have? C1 here. So this one is 3. This one minus 3 and this one 3. Okay, so along the C1, so we have x equal to 3. So the equation is x equal to 3. So since in the equation there is no z, only x and y, so we can use x and y instead of convert to the parametric equation. So x equal to 3, so y, that line is located on y equal to 0. Y equal to 0, so dx is 0, dy is 0. Okay, so so we know that r is in terms of x and y in general. So when we have dr, so we have dx and dy. Okay, so what is your f? F in this case, the f is given by z, xy, and then xz. So for the first one, f dot dr is given by z dx. Okay. Okay. So f dot dr, f z multiplied by dx. Actually, we have the 3D. So when we have a 3D, should have the component z as well. So we got this z here. Okay. So first component x, z multiplied by dx, xy multiplied by dy, xz multiplied by dz. So now we just put in our okay, dx is 0, so we got 0 plus dy also 0 plus x is equal to 3, so 3z dz. Okay, so our first line integral along the C1 is now becomes 3z dz. Okay, so now look at the limit of z. So z is 4, right? 4 to 0. You have to follow the direction 4 to 0. Okay, 4 to 0. So 4 to 0 meaning that 4 to 0. Your initial is 4 and your terminal is 0. Okay. So we integrate 3 over 2 z square 0. So negative, we got negative 3 over 2, 0 minus 16. Negative 24. You have to follow the direction, even though it looks 4 to 0 is something contrary, but you have to follow the direction. Okay, 4 is your initial, 0 is your terminal of z. Okay, so that is for C1. So now we look at the C2. What is the information that we got from C2? So now we work on C2. So what is the C2? C2 in this case is, you can see that one is z equal to 0. Okay, z equal to 0. The line of z equal to 0. So, and also y equal to 0, right? You can see this one, z equal to 0 and also y equal to 0. So along that line, you can see that z equal to 0 and also y equal to 0. So your dz is 0 and your dy is 0. So then f dot dr, so we have the sim f, so using the sim f, where is your f just now? Have it up here. So z, okay, so here f dot dr, z dx, xy dy, at z dz, which is, it is multiplication of all the component of f and the dr. So from here, z equals z0, y0. So z0, so this one 0. Y0, so dy 0, so this one 0. And dz also 0. So your expression f dot dr is 0. So when you put into the integral, and the answer will be 0. Okay, so that is C2, you got 0, and C3. So what you can see on the C3, the curve C3 here is x equal to, so x equal to at the back here, so this line is lying on x equal to minus 3. So the equation there is x equal to minus 3, and what else that you can say there? Also y equal to 0, because it is lying on the wall. This is a wall when y equal to 0. So y equal to 0. Y equal to 0, so your dx is 0, then dy also 0. Okay, so then we put into the f dot dr, where we have this same. So z dx plus xy dy plus xz dz. And then we substitute dx 0 and dy also 0. And we have minus 3z dz. Negative 3z dz. So on the C3, f dot dr is negative 3z dz. Okay, look at the limit along the C3. So z from 0 to 4. Zero to 4. Okay, 0 is the initial, 4 is terminal. So when we integrate, we got negative 3 z squared over 2. 0 to 4. And you will get, okay, you got negative 24. So that is the C3. So now look at C4. Where is C4? So C4 here, this one. So C4 is located on z equal to 4 and y equal to 0. Z equal to 4, y equal to 0. Okay, Z4. So z equal to 4, y equal to 0. dz is 0 and dy is 0. So we plug into the f dot dr. So z dx plus xy dy plus xz dz. So 4 dx dy is 0, dz also 0, so you got 4 dx. Okay, so now your line integral along the C4, this will give you 4 dx. And what is the limit along the C4? We have to check from the sketching. So from here to here, so x from minus 3 to 3. Minus 3 to minus 3 to 3. So 4x minus 3 to 3 for 3 plus 3. We got 24. Okay, then we have to total up all the C. This one. Okay. So C1 just now we got minus 24. C2 we got 0. C3 we got minus 24. C4 we got 24. So when we total them up, the answer is minus 24. So this is the result of the evaluating the surface integral using Stokes theorem, where you need to obtain instead of obtaining the surface integral, whereas asking here, using Stokes we compute the line integral, but you have to provide 4 line integral, and the answer is minus 24. Okay, so I just want to stress out here. So it depends on the instruction. If the instruction don't mention that you have to use the Stokes, then it is up to you. You want to proceed using surface integral, or you want to apply the surface integral as mentioned here using Stokes, where you have to provide the line integral. Okay, so you have an option if they don't mention that, but if they put the instruction using Stokes theorem, evaluate this one, then you have to provide me like this. You have no option. You have to provide the line integral in your calculation because they ask for Stokes theorem. But if the instruction like this, then you can proceed to give the calculation using surface integral as stated here, or you can use Stokes theorem by providing me this calculation, which is line integral. Okay.